So now, instead of considering the line integral only over a path C, now we're going to consider the idea of a line integral of a vector field along the curve. For our definition, let F be a vector field with continuous components that are defined along a smooth curve, C, parametrized by R, over the interval where t is between a and b. So then the line integral of f, the vector field f along the curve C, that line integral along the curve, is actually f, the vector field, dotted with t. T is the tangent unit vector, and then we're integrating with respect to arc length. Now, remember, t is the derivative of r with respect to s. So we can simplify this to the line integral across the curve of f dotted with dr. So defining f in this manner, and then that derivation of the tangent unit vector into dr ds, we learned about that previously, but I've kind of written that out for you here. So let's think about what this means and how we are going to evaluate the line integral. To evaluate the line integral of the vector field f along the curve C, represented by this parametrized curve, the first thing we're going to do is to create a composition. So we'll express f along C as f composed of r of t. So plugging in or subbing components into those three multivariable functions, m, n, and p. The second step would be to find that velocity vector, the derivative of r with respect to t. And then the last third step here is to evaluate that line integral with respect to the parameter t. So what this means is the integral from a to b of f of r of t dotted with the derivative of r with respect to t dt. So you can see that simplification there. That's why we don't have the dt in this notation. So this is really what we're going to be doing, or rather calculating. All right, so this is our setup for our calculations. Now let's look at an example. For this example, we're given the vector field f, denoted by xyi plus yzj plus xzk. We want to find the line integral from 0, 0, 0 to 1, 1, 1 along the curved path C. C is denoted by the parametrized vector r of t equal to ti plus t squared j plus t to the fourth k, where t is between 0 and 1. So a couple of things. R, we could write that shorthand. We've got our x component t, our y component t squared, and our z component t to the fourth, or as defined, g of t, h of t, k of t. And then we have an m and an n and a p up here. We want to plug these x, y, and z components into f. So that means f equals t times t squared I plus t squared times t to the fourth j plus t times t to the fourth k. Or rather, f equals t cubed I plus t to the sixth j plus t to the fifth k. And we can rewrite that using our shorthand notation. I think it's a little less confusing when we're thinking about a dot product to have it in that manner. So then dr dt, that's just going to be derivative of each of these components. We have 1, 2t, and 4t cubed. Then that means f dotted with dr dt will multiply and then add each of these three components. So I'll have t cubed plus 2t to the 7th plus 4t to the 8th. So I've done three things here. I found my composition, f composed of r. I found the derivative of my r vector, my velocity vector, and then I dotted those two vectors. So we can interpret this as the line integral along the path C of f dotted with dr, or rather the integral from t equals 0 to t equals 1 of t cubed plus 2t to the 7th plus 4t to the 8th dt by our definition. And this is very easy for us to integrate. So I have 1/4 t to the 4th plus 1/4 t to the 8th plus 4/9 t to the 9th evaluated between 1 and 0, and that gives us 17/18. So that is the value of the line integral for this vector field along the path or the curve C, which is parametrized by R.